Welcome to Review Lecture 4.2 on current. Upon completion, you should be able to define electric current, calculate electric current, and if you're a Physics 222 student, which is calculus-based, you should also be able to define current density. Now, the flow of charge is current. Heat flows through a conductor when a temperature difference exists. Heat will flow from the higher temperature to the lower temperature. When temperature is at equilibrium, the flow of heat ceases. Charge flows in a similar way. Actually, in metals, they both utilize the free electrons to accomplish this. Charge flows when there is a potential difference or difference in potential, that is voltage, between the ends of a conductor. It's a little bit more complicated because charge comes in negative and positive flavors, whereas thermal energy only comes in one flavor. However, the flow continues until both ends reach the same potential. When there is no potential difference, the flow of charge through the conductor stops. To attain a sustained flow of charge in a conductor, one end must remain at a higher potential than the other. Now, the flow of current is a lot like water flowing through pipes. Water flows from a higher pressure to a lower pressure. The flow will cease when the difference in pressure ceases. Water will continue to flow if there's a difference in pressure, as long as that difference in pressure is maintained with a pump. The same is true of electrical current. Often we use the analogy of water flowing through pipes as a model for electricity flowing through wires, and this has been around since Ben Franklin's day. So in this circuit here, the pump would be like a battery, the pipes would be like wires. The tank would be like a capacitor. The restriction in its tank would be a resistor or load. What happens when the ends of a conductor are different electrical potentials? When the ends of a conductor are different electrical potential, the charge will flow from one end to the other, from the high potential to the low potential. While the current is flowing, negative electrons will swarm through the atomic network of positive charge atomic nuclei. Under ordinary conditions, the number of electrons in the wire is still equal to the number of positive protons in the atomic nuclei. As the electrons flow, their number entering is the same as the number leaving. So in other words, out equals in. So the net charge is normally zero at every moment. Now, this is Physics 222. If you are an algebra-based physics student, in other words, Physics 122, please skip ahead to slide 8. Okay, back to Physics 222, calculus base. In Figure A, any isolated conducting loop, regardless of whether it has an excess charge, is completely at the same potential. In other words, it's an equal potential surface. No electric field can exist within it or along its surface. In Figure B, we have inserted a battery into the conducting loop. Now the conducting loop is no longer at a single potential. In fact, the positive battery terminal has a higher potential than the negative one. And by the way, don't do this. This is a great way to start a fire. Electric fields can act inside the material, making up the loop, exerting forces on the external charges, causing them to move and thus establishing a current. Now we've taken a section of a conductor that's part of a conducting loop in which a current has already been established. If a differential charge dq passes through a hypothetical plane such as AA prime in time dt, then a current I through the plane is defined as I equals the derivative of q with respect to time, or I equals dq dt. The unit on that is the ampere. 1 ampere is 1A here, that's a symbol. That equals 1 coulomb per second. For a constant current, which is the usual case, this can be written as I equals q over t. If you are a calculus-based physics student, please skip to slide 9. If you're an algebra-based student, Physics 122, this is where you want to be. In Figure A, any isolated conducting loop, regardless of whether it has an excess of charge, is completely at the same potential. In other words, it's an equal potential surface. No electric field can exist within it or along its surface. In Figure B, if we insert a battery in the loop, the conducting loop is no longer at a single potential. The side that's connected to the positive terminal is now at a higher potential than the side that's connected to the negative terminal. Safety tip, do not do this. It's a great way to start a fire. Electric fields act inside the material that makes up the loop, exerting forces on the internal charges, causing them to move and thus establishing a current. In Figure C, a section of the conductor, which is part of a conducting loop in which current has already been established. If charge delta Q passes through a hypothetical plane, such as AA prime and time delta T, then the current I through that plane is defined as I equals the limit as delta T goes to 0 of delta Q divided by delta T. The units on that are the new units. 1 ampere, which is 1A, equals 1 coulomb per second. The average current is delta Q over delta T. Of course, the units are the same. For a constant current, which is the usual case, this can be written as I equals Q over T. Now, the electric current in units. The electric current is measured in amperes. We give it the symbol A. An ampere is a flow of 1 coulomb of charge per second. So 1 amp equals 1 coulomb per second. When the flow of charge past any cross-section is 1 coulomb, which is 6.24 billion electrons per second, The current is 1 ampere. An ordinary old-fashioned 100-watt light bulb will draw a current of 0.83 amps. That means it takes about 1.2 seconds for 1 coulomb of charge to flow through that bulb. Now, Avogadro's number. Recall from physics and chemistry, Avogadro's number. Na is 6.02 times 10 to the 23rd molecules per mole. The number of molecules is the ratio of the mass of the sample, MSAM, to molecular mass, big M, times the Avogadro's number. So N equals MSAM divided by big M times Na. Or N, this is capital N, equals little m over big M times Na. Just to keep continuity, you may use little m in place of MSAM. Unfortunately, this is another overused symbol. Yeah, it stands for mass, it stands for molecular mass, it stands for meters, so it's a pain. Typically, most textbooks use little m to represent molar mass, which is mass of one molecule, when they discuss Avogadro's number. The way out of this situation is to always check the units. Now, here's another situation, the universal variable and its griefs. The symbol little n is used throughout physics. It's overused as the other universal symbols such as K, L, D, and C. It represents more than one characteristic, that is, it has different units. And the units are the best way to keep it straight. For instance, for Avogadro's number, little n is big N over Na. That is, little n is then the number of moles. The units of that would be the mole. Charge, Q equals N times E. N here is the number of carriers of a charge E. The units on that is usually electrons. Carrier density, this is physics 222, calculus-based physics. J equals NeVd. N here is the number of carriers per unit volume. And the units on that are electrons per cubic meter. Units, units, units. You must put full units on your numbers and cancel them properly. If you do that, there shouldn't be any fuss on this. If you don't, it'll be endless tears, cursing, frustration, and bad grades. This is where people fall apart in this class, and this is where the memorizers don't do well. Because if you try to memorize your way through these equations, you're using the same symbol 3 different ways, and you're not going to be able to do that. So you have to do your homework, you have to practice, you have to write down units, and make sure you understand the units. You can't just memorize your way through this or cheg it or anything else like that. So please make sure you're doing your homework. That's a warning. Okay, checkpoint, circuits and current. A complete closed circuit is one where the current can flow all the way around. Now, this is a complete circuit. Here's a battery connected to a light bulb, and there's 2 wires. One runs from the positive terminal through the light bulb back to the negative terminal. The battery and the electrons can go around and around. Here's the schematic of that. This is the battery. This is the device. That's the bulb. Here's the wiring. So this is a complete closed circuit. The current can flow all the way around. Now, notice that the schematic really doesn't look much like the physical circuit. Now, in order for current to flow, there must be a complete path from one battery terminal through the circuit and back to the other battery terminals. Only one of these circuits satisfies that condition, so only one of these will work. Which one is it? Well, if I look at this, I can see this is not connected to the negative terminals. This is not a complete circuit. This ditto for this. This one, the current can flow from the positive terminal through the light bulb back to the negative terminal. So this one is complete. So C is the correct answer. We're going to talk about current through a junction. A junction is a point where more than 2 wires meet. So in figure A, a conductor with an incoming current I0 is splitting in a junction with 2 branches with outgoing currents I1 plus I2. Charge is conserved, so summation In equals summation I out. What I like to say, in equals out. So in this case, I0 equals I1 plus I2. It does not matter if you bend or reorient the wires in space. It does not change the validity of this equation. Current arrows show only a direction or sense of flow along a conductor. They are not a direction in space. The current arrow is not a true vector. Current is drawn in the direction in which hypothetical positive carriers would move, even if, as the usual case, the actual charge carriers are moving in the opposite direction because they are negative. This flow of hypothetical positive charge is called the conventional current. For a current of electrons, the direction of the conventional current is opposite of the flow of the charges. Now, in most cases, this does not matter. We just remember it and ignore it. So here's a device connected to a battery. The flow of the electrons, which are negative charges, is from the negative terminal of the battery through the device, through the circuit, and back to the positive terminal of the battery, and then through the battery to the negative terminal. The flow of conventional current is from the positive terminal of the battery through the device and the circuit back to the negative terminal of the battery, and then through the battery itself. But in most cases, this does not make any difference. Okay, even on a quantum mechanical level, the flow of positive charge in one direction is fundamentally pretty much the same as the flow of negative charge in the opposite direction. Okay, now this is a Physics 222 problem. In other words, you should, if you are a calculus-based student, you should be paying attention to this. If you're an algebra or Physics 122 student, please skip ahead to slide number 18. Water flows through a garden hose at a volume flow rate of dVdt of 450 cubic centimeters per second. What is the current of negative charge? Physics of this is the current is the rate at which charge passes a point. The current I of negative charge is due to the electrons in the water molecules moving through the hose. The current is the rate at which that negative charge passes through any plane that cuts completely across the hose. The unknowns are the dVdt, which is the volume flow rate, is 450 cubic centimeters per second, and we convert that to SI, 450 times 10 to the minus 6 cubic meters per second. The molecular weight of water is 0.018 kilograms per mole. You can look that up off the periodic chart or in a chemistry book. Little n over big N is 10 electrons per water molecule. Rho, which is the density of water, is 1,000 kilograms per cubic meter. What is the current? The formula are Q equals NE times E, I equals dQ dt, big N equals little m times NA over big M, rho equals M over V. Where little n equals Ne, that's the number of electrons, big N is the number of water molecules, big M is the molar mass, little m is the mass, Na is Avogadro's number, and that'll be in water molecules per mole. Note, I put full units on everything. Identify exactly what I'm talking about. Little n divided by big N is the number of electrons per water molecule. That, of course, will be 18. E, which is the charge on the electron, is 1.60 times 10 to the minus 19 coulombs per electron. Okay, so we have some formulas here. Q equals little n times E, and that equals little n over big N times E times big N. I is dQ dt, that equals little n over big N times E times the derivative of big N with respect to time. So dN equals Na over big M times dm, and that will equal Na over big M times rho dV. I then will be little n over big N times E times the Na divided by big M times rho dV dt. Now we stick numbers in, and notice I put full units on everything. So the current is 10 electrons per water molecule times 1.6 times 10 to the minus 19th coulombs per electron times 6.02 times 10 to the 23rd water molecules per mole divided by 0.018 kilograms per mole for water times the density of water, which is 1,000 kilograms per cubic meter, times 450 times 10 to the minus 6 cubic meter per second. That's a flow rate. And here's a units conversion, 1 amp second per coulomb. Now, we want to make sure the units cancel out. So I'm going to go through, and what we want to come out with is amps. We make sure we come out with amps. Okay, the electrons here cancel with the electrons there, and that's a unit. The water molecules cancel with the water molecules here. These moles cancel out. The coulombs will cancel out over here. The kilograms will cancel out there. The cubic meters here cancels out here with this cubic meters. The seconds cancels out here. The only thing left is amps. Do it this way. If you do not do it this way, all this confusion where N can stand for 3 or 4 different things, you've got a big M and a little m, and it can stand for different things, will get you completely messed up. Do it this way. In fact, the way I do this is I start at one end, and I just put the units together until they work. And usually that works out really well, and then I check and make sure it makes sense. Okay, now this would be actually, the current ends up being 24 million amps, and a full units check came out okay. Now, actually, this would be canceled by the equal number of positive charge, the water molecule nuclei flowing in the same direction. Otherwise, you'd be electrocuted in your shower. Okay, now if you're a Physics 122 student, you should be here. If you are an algebra-based student, if you're a calculus-based student, please skip ahead to slide number 21. Okay, water flowing through a hose for a algebra-based Physics 122 student. Water flows through a garden hose at a volume flow rate of delta V over delta T of 450 cubic centimeters per second. What is the current of negative charge? The physics of this is the current is the rate at which charge passes a point. The current I of negative charge is due to the electrons in the water molecules moving through the hose. The current is the rate at which that negative charge passes through any plane that cuts completely across the hose. The knowns and unknowns. Delta V, delta T, that's the volume flow rate, is 450 cubic centimeters per second. We want to immediately convert that to SI. That's 450 times 10 to the minus 6 cubic meters per second. The molecular weight of water is 0.018 kilograms per mole. You get that off the periodic chart or look it up. The little n over big N is 10 electrons per water molecule. The density of water is 1,000 kilograms per cubic meter. What is the current? The formula is Q equals little ne times E, I equals delta Q over delta T, big N equals little m times Na divided by big M, and rho equals M over V, where little n equals Ne, that's the number of electrons, big N is the number of water molecules, big M is the molar mass, little m is the mass, Na is Avogadro's number, and written in terms of 6.02 times 10 to the 23rd water molecules per mole. Identify exactly what you're talking about here, or you'll get confused. Little n divided by big N is the number of electrons per water molecule. And little e is the charge on the electrons, 1.60 times 10 to the minus 19 coulombs per electron. Okay, so we know that Q equals little n times E. That will equal little n over big N times E times big N. I is delta Q over delta T. That will equal little n over big N times E times delta big N delta T. Delta N is then Na over big M times delta M, or that equals Na over big M times rho delta V, that should say delta V. I then equals little n over big N times E times Na over big M times rho delta V delta T. So now we can start putting in numbers, and notice I put full units on everything. So I will then be 10 electrons per water molecule times 1.60 times 10 to the minus 19 coulombs per electron times 6.02 times 10 to the 23rd water molecules per mole divided by 0.018 kilograms per mole for water times 1,000 kilograms per cubic meter times 450 times 10 to the minus 6 cubic meters per second times the units conversion. Now, I want amps to come out. I'm going to check and make sure all the units come out correctly. I start at this end. I have 10 electrons. Okay, and I'm looking for electrons. There's electrons. So it cancels out. That is a unit. And you should treat it like this. I have water molecules. Here are water molecules. That cancels out with the water molecules here. I have coulombs. Coulombs cancels out over here. Okay, moles cancel out here. Kilograms cancels here. Cubic meters cancels there. And seconds cancels there. What's left behind is amps. And the current is 2.4 times 10 to the 7th amps. The full units check is okay. Now, I want you doing units check like this, because if you don't, with the confusion of having 3 different things that stand for N, 2 different versions for M, and all these different units and everything else like that, if you don't write it out like this, you try to memorize your way through this stuff, you're not going to make it. I guarantee it. I've seen this happen before. Now, this is a very large current. It's 24 million amps. But this is canceled by an equal amount of positive charge, the water nuclei flowing in the same direction. Otherwise, you'd be electrocuted in your shower. So it's a good thing things are basically electrically neutral. Now, what is really going on inside the conductor? We're going to put a potential difference across this conductor. We're going to put the positive side on the left side, the negative side on the right side. Immediately, the minute you do this, you'll end up with an electric field inside the conductor. In this case, it's going to point from left to right, because it's going to go from positive to negative. Now, the electrons, being a negative charge, will swim upstream against the electric current. They're going to go from negative to positive. And instead of going very quickly, they actually have a hard time getting through this material. They're jiggling around, they're zooming around in here, and they don't go straight. Instead, they bounce off of other particles, and they have collisions with atoms and other electrons. So they basically are zigzagging around in here. So their drift speed is relatively slow. In fact, it's extremely slow. The electrons in a conductor have large random speeds just due to the thermal temperature. But when a potential difference is applied, the electrons also acquire a very tiny average drift velocity, which is much, much smaller than the random thermal velocity. Now remember, the conventional current goes from positive to negative, but the direction of the drift speed goes from negative to positive. Remember, electrons swim upstream. So here we have a cross-section of wire. Okay, we have a wire, a circular wire. The electric field is to the left. The electrons are moving to the right with a drift speed Vd. Okay, and there's a certain cross-sectional area of the wire, and that will include a volume A times X, where X is this distance here, and X equals Vd times T. So the charge on the wire, Q equals NE times E, that will equal N, which is the number of charge carriers per volume, times the area times the length of the wire, times the charge on the electron, where X and L are the same here. Where N, of course, is the number of charge carriers per volume, and that's the electrons per volume. And the volume in here is area times length. The charge on the electron is 1.60 times 10 to the minus 19 coulombs per electron. The velocity distance time relationship where X equals L, L equals VT, or T equals L over VD. So then the definition of current, we're going to assume it's constant, I equals Q over T. Plug things in, you end up with N times A times L times E over L over VD. We can simplify and solve this for velocity, and that will be the drift speed. VD, which is the drift speed, equals the current divided by the number of charge carriers per volume times the cross-sectional area of the wire or conductor times the charge on one electron. So VD is equal to I divided by N times A times E. Okay, here's an example of drift speed in a wire. What is the drift speed of the conduction electrons in a copper wire with a radius of 900 micrometers when it has a uniform current of I equals 17 milliamps? Assume that each copper atom contributes one conduction electron to the current, and the current density is uniform across the wire's cross-section. Okay, the physics of this is a drift speed problem, the knowns and unknowns. We know the radius of the wire, and we're going to convert that to SI units. It's 900 times 10 to the minus 6 meters. The current is 17 milliamps. We're going to convert that to SI units, which is 17 times 10 to the minus 3 amps. Molecular mass, big M, of copper is 63.54 times 10 to the minus 3 kilograms per mole. You can look that up. The density of copper is 8.96 times 10 to the third kilograms per cubic meter, and we need to find the drift speed. The formula is drift speed is current divided by N times A times E. So that would be N, which is big N, equals little m over big M times NA, and rho equals m over V, and A equals pi r squared. Little n is the number of electrons per volume, big N is the number of atoms, big M is the molar mass, little m is the mass, and A is Avogadro's number, which is 6.02 times 10 to the 23 particles per mole. We can solve this for VD. VD is I times big M divided by NA rho E pi r squared. Now we can plug in numbers. So the current is 17 milliamps, or 17 times 10 to the minus 3 amps. The big M is 63.54 times 10 to the minus 3 kilograms per mole. There's the units conversion factor here to make sure we keep the units straight. And then we're going to divide by NA, which is 6.02 times 10 to the 23rd electrons per mole, times, and we're also dividing by rho, and that is 8.96 times 10 to the third kilograms per cubic meter. And then we have, the charge on the electron down on the denominator here. It's 1.60 times 10 to the minus 19 coulombs per electron times pi, still down in the denominator, also divided by 900 times 10 to the minus 6 meters squared. That is the radius squared. VD is 4.9 times 10 to the minus 7th meters per second. Now we're going to check our units. We want to end up with meters per second. We have amps here, that'll cancel the amps there. Okay, we have kilograms here, that'll cancel this kilograms. This mole will cancel that mole. Okay, the electrons, E, will cancel this E. The coulombs here cancels that coulombs. And we wind up, we have meters cubed on the bottom here, and we have meters squared. When you do this, it'll end up as 1 over meters. If you take 1 over meters, you wind up with meters, and we have seconds left over, so it's meters per second. And the full units check came out correctly. Make sure you do it this way. I guarantee if you don't do it this way, you're going to have problems. Now we have a set of currents flowing in various branches here. What is the current in branch B? Well, in equals out. So we have 5 amps coming in, we have 1 amp going out. So this means we also have to have another 4 amps going out. So B is 4 amps, and it would be to the right. If you look at this, the correct answer is not given and to the right. So sometimes not given is the correct answer. Please don't pick it by default. In which one of the following situations does conventional current flow due north? Okay, now, conventional current is a flow of hypothetical or real positive charges. So what we're looking for is either a positive charge flowing due north or the opposite, which is a negative charge flowing south. One is incorrect. Water molecules are neutral. Electrons in a beam are moving due south. Well, that's a negative charge moving south. That's one's looking pretty good. And always read the whole thing. Electrons in a wire connector battery are moving from south to north. That's incorrect. So the correct answer to that one is the electrons in a beam are moving due south. The direction of the conventional current is opposite the direction of moving negative charges. When positive lightning, which is a very rare form of lightning that originates in the positive cloud tops, strikes, the electrons flow from the ground upward to the clouds above. What is the direction of the electric field of the lightning? Also, which way would conventional current flow? Well, it is downward. Remember, electrons swim upstream against the direction of the electric field. So the top of the cloud is positive and the ground under it's negative. So it means the electric field is flowing from the positive charge to the ground, from the top down. The electric field is downward. The electrons are going to be moving opposite to that. They're going to swim upstream, so they're going to flow upward. They would be more attracted to the positive cloud tops. So they're going to flow toward the positive cloud tops, so it'll be upward. The conventional current would flow downward, just the opposite of the way the electrons flow. And the conventional current flows in the same direction as the electric field. Which one of the following statements concerning the electric field inside a conductor is true if the electrons are moving from right to left in a conducting wire? Well, we can eliminate this right off the bat. If they're moving, the electric field is not zero. The electric field cannot be directed perpendicular to the direction of electrons because they're moving toward the left. Okay, so the electric field is going to be pointed toward the right. So the electric field is going to be pointed opposite to the direction the electrons move. Remember, they like to swim upstream. Suppose a current-carrying wire has a cross-sectional area that gradually becomes smaller along the wire, so the wire has the shape of a very long truncated cone. How does the drift speed vary along the wire? It will speed up as the cross-section becomes smaller because VD is proportional to 1 over the cross-sectional area. So as the area gets smaller, VD increases. And that makes sense. At this point, if you're an algebra-based physics student, that is Physics 122, you're finished with the lecture. Thank you. If you are a calculus-based physics student, that is Physics 222, we have one more topic for you, only 4 more slides. The topic is current density in a wire. The current density J in a wire is the current per square meter of cross-sectional area A. So J equals current density equals I over A equals NE times E times VD. I, of course, is the current in amps, A is the cross-sectional area in square meters. NE is the number of charge carriers per cubic meter, that is carriers per cubic meter. E is the charge in coulombs on one charge carrier, that is coulombs per carrier. VD is the drift speed of the carriers in meters per second. The current density, as you can see from these units, has units of amps per square meter. The current I as a scalar quantity is related to the current density J, which is a vector quantity, where I equals the integral of J dot dA, or I equals JA, where dA is the area vector. That is a vector perpendicular to normal to a surface element of area dA. Remember, angles are normally measured relative to the normal. And the integral is taken over any surface cutting across the conductor, a surface through which the charge carriers are moving. Now we'll talk about some density directions and what happens when the cross-sectional area of a conductor changes. So in this picture up here at the top, the electric field is pointing to the left in the wire in the picture. In the wire, of course, the electrons are moving to the right. They're swimming upstream. The conventional current is moving to the left. And J and VD point toward the left by convention. In other words, they follow the direction of the conventional current, which remember is the flow of hypothetical flow of positive charges, or the flow of hypothetical positive charges. As the charges flow through the narrow restriction, charge is conserved. IN equals I out. They don't bunch up here. They got no place else to go. The amount of current does not change. The current density and the drift speed both increase as the area decreases. A is the current density. That equals I over A equals NE times E times VD. I, NE, and E do not change. A, VD, and J do. And J is inversely proportional to the area, and VD is also inversely proportional to the cross-sectional area. Okay, our last checkpoint. The current density in this wire is, now, current density is current divided by cross-sectional area. And you're going to have to convert this area to SI, because it's in terms of amps per square meter. So we take the 8 amps of the current and divide it by 0.002 meters quantity squared, and that is 2 times 10 to the 6 amps per square meter. Thank you.